Assalamu alaikum. This is Maria here, and I am the student of MS Chemistry studying at UMT. Today, the topic of our discussion is the geopolymer and sustainable cement. Secondly, we'll talk about the digital transformation in cement industry. Thirdly, we have the life cycle assessment occur by the passage of time and its impacts on our society. These are the contents of our topic, which include abstract introduction, geopolymer cement, and then digital transformation and cement industry, digital solution for the cement industry, and then we have some key points. After that, we'll discuss about life cycle assessment and environmental impact. So now we'll move to our abstract. World's population has increased, so that's why the demand of cement for building also increased. At present days, geopolymer cement made up of various raw material they have high amount of sodium sulfate, aluminum sulfate, and uh, sodium hydroxide. They solve many problems. These are involved as an eminent material for the purpose of sustainability. Geopolymer cement are or these raw material are preferred due to their lesser emission of harmful gases, as the Portland cement include these gases in large quantity. Also, the durability of geopolymer cement is highlighted. Now, uh, environmental impact of cement also concerned. Life cycle assessment evaluate its impact throughout its production process. This analysis was carried out all over the world, including many countries like India, China, Europe, UK, and so other countries. Now we have introduction. Cement or concrete and other resources are used for the building purposes for the development of countries' construction means. But the manufacturing of concrete produces a large amount of carbon dioxide that around our surrounding. It could be around 30%, and which is highly dangerous for human health. Emission of carbon dioxide is the result of grinding or burning of fossil fuels and raw material in kiln chambers. This emission affect the environmental condition and generate global warming and also the melting of ice in different regions. However, knowing its adverse side, cement utilization increases in the building construction industry around the globe. Cement binder production vary in different countries around the world. The variation in cement production is due to the availability of resources or other raw materials. The majority of the countries have their resources by which cement production and its need for construction is achieved. Manufacturing cement directly or indirectly emits gases like carbon dioxide, which has an adverse effect on the environment. The calcination process and burning of raw material are classified as the main sources of gaseous emission. Emission of carbon dioxide during cement manufacturing is an alarming situation around the world, and hence measurement is needed to minimize carbon dioxide emission. This Before providing a summary of available evidence on geopolymer behavior, it is worth reviewing recently reported research on related issues in the recent years. Although many reviews are available on the geopolymer composites and they mainly focused on the general application of geopolymer composites reinforced with cellulose fiber, synthetic fiber, and fabrics. Many reviews are present on the history, background, and characterization, also sustainability and various factors that affecting the final properties of geopolymer composites. Still, the literature lag in providing a comprehensive review on the new type of precursor-based geopolymer composites, that is, fly ash-based polymer composites. Recently, new information has been added to the literature about the geopolymerization process and precursors that affect the properties of such composites. In addition to this, the application and challenges of geopolymer composites on a large scale need to be addressed. After introduction, our next part is geopolymer concrete. The geopolymer cement or concrete has a high quantity of aluminum silicate, and also its characteristics are similar to the cement family. These composites are unreactive in the presence of water and needed an alkaline medium to perform well. Also, these alternative binders have load-bearing ability by forming 3D structures when these are placed in alkaline binder. Now, we'll talk about the digital transformation in cement industry. Environmentally driven geopolymer applications are based on the implementation of potassium calcium polysilicate siloxo and potassium calcium polysilicate disiloxo cement. In industrialized countries, emphasize its put on toxic waste and radioactive waste safe containment. On the opposite, in emerging countries, the application relate to sustainable development, essentially geopolymeric cement with low carbon dioxide emission. Both fields of application are strongly dependent on politically driven decisions. Now, there are some steps for the solution of cement industry. These include, firstly, it is predictive maintenance. Poor maintenance often lead to a almost 5 to 20% downgrade in a plant's overall productive capacity. Maintenance allow plant operator to monitor each installation's integrity and assess the probability of breakdown, which enables timely addressal of maintenance issues. Beside preventing extended downtime, it helps improve operational efficiency, reduces maintenance cost, and limit wear and tear of machinery. In predictive maintenance, the operator heads production for a few minutes each month to replace equipment based on its health as opposed to routine periodic replacements. Predictive maintenance is particularly useful for gearboxes, mill and kiln related installation in a cement plant. Now the second step of a digital solution is digital twin. A digital twin allows a cement company to mirror their entire production process or a portion of a digital model, referred to as twin of the plant's physical assets, process, and systems. AI, artificial intelligence, and machine learning is used to optimize the manufacturing process as the model evolves. user get data without frequent reprogramming. Now, third point is predictive quality analytics. It allows company for the accuracy of cement quality. These models help manufacturer to choose alternative approach, such as high grade limestone. They use a range of alternatives approach. Predictive quality analytics use machine learning algorithm to correlate the quality of production, and artificial intelligence enable a system to learn over the period. Now, the fourth point is alternative fuel optimizer. Alternative fuel is identified as a potent decarbonization lever and can significantly help reduce the expenditure on energy in cement production. The uptake of alternative fuel in India is yet to reach its true potential due to quality variance, dispersed supply stream, and low value density with logistics. Alternative fuel optimizer enables cement manufacturers to manage the inherent variability of alternative fuels, especially its physical and chemical properties such as calorific value and compatibility of fuels. Now the fifth step is integrated control tower. This tower allows operator to remotely run their cement plant from a central office by reducing operational and maintenance cost, optimizing workforce and improving health and safety performance. An integrated control tower can monitor equipment condition, predict failures, plan maintenance, operation, and choose optimal settings and inputs. It is often enabled with scenario analysis software that help in implementing the process at an optimum level. A control tower can enable a company to realize almost 5 to 10% improvement in on-time delivery performance and 10 to 20% reduction in distribution cost. Now, the sixth step is digitalization of cement value chain. Digitalizing upstream and downstream supply can help in improving visibility on raw materials, fossil fuels, and finished goods, deliver quality customer service, and optimize cost. Tagging trucks with the global positioning system helps in encouraging responsible behavior among drivers minimizes deviation from set paths, thereby reducing turnaround time and safety incidents. Now, the other step is application of geopolymer cement in building sectors. These include heavy metal waste encapsulation, then we have uranium mine tailings and radioactive sludge. After that, greenhouse carbon dioxide mitigation, low carbon dioxide geopolymer cements. First, uh, as a geopolymer, cement has been used in various commercial applications due to its rapid mechanical strength, keen thermal and chemical resistance, aggregate adherence, and enhanced toughness. Rapid strength gain up to 50 MPa and high resistance against sulfate attack has been geopolymer cement as one of the substitutes to the OPC concrete. Concrete utilization in the construction industry has been increased in recent years, and it is posed that its value will be further increased in the future. Heavy metal waste encapsulation is an application of geopolymer cement. Uh, this application is started in different countries all around the world, and it was dedicated to the stabilization of based metal mine tailings. The result of a laboratory were excellent, yet the experimentation stopped because of lack of political support. Then we have uranium mine tailing and radioactive sludge. This application was started in 1994, funded by the European Union. This project was aimed at manufacturing cost-effectively new geopolymeric cement. It was experimented on two important uranium mine locations: material characterization and mix design. Uh, Advanced applications or technologies like 3D printing, smart sensor, and autonomous robots, etc., have already been used in various industries. While on the other hand, the cement and concrete industry is far behind due to the lack of acceptance, related cost, and other expertise. Concrete itself has gone a tremendous development path over the past few decades. Cement has been partially or fully replaced with several types of byproduct or to enhance some properties and to increase its sustainability. Concrete consists of binder and fine aggregate, water, and other mixtures, and wet adhesives. These materials are characterized by chemical composition, surface area, texture, and amount of intermixed fine and coarse aggregates. These properties affect the mix design and behavior of concrete during mixing and casting, and later determine hardened state properties and often also durability. Now, concrete properties include the concrete temperature. The temperature of fresh concrete and the ambient temperature are very important parameter while designing concrete mixture or planning, transporting, casting, and curing. Generally, high temperature accelerate the hydration process, which might require addition of retarder, decreasing the amount of cement and addition of certain secondary cementitious materials. On the contrary, a lower temperature slows down the hydration process and delays strength development. So, digitalization of concrete temperature measurement is advanced. State-of-the-art technologies with the embedded sensor have been used. One common technology used to monitor the temperature is thermal imaging using infrared thermography. Uh, this technology is non-destructive, but it is applicable only to concrete not exposed to sunlight. Other techniques included, for example, fiber bed grating sensor, which are used to monitor temperature and shrinkage at the same time. It might be difficult to achieve due to this, for example, foam cover or other material present on the concrete surface. To overcome this drawback, automatic wireless sensors were used, but about 5-degree discrepancy was observed between actual and experimental values. Sensor utilizing passive radio frequency identification and radio frequency integrated circuit enabled short-range remote sensing and achieved the detection of resolution of about 0.25 degree. Now, the second point is workability. Workability is an essential technological property of concrete, controlling the casting process and affecting the quality of produced concrete elements or structures. It can be measured, for example, by slump or slump flow combined with T50 time. In the case of self-compacting concrete, a number of digitalizing solutions have been introduced, and the artificial neural network is one of the examples. Uh, they produce a more accurate prediction of workability than the nonlinear regression analysis, and it has the ability to model the slump for any mixed design. This graph shows expansion on a y-axis and days on x-axis. These are the differences between two cements. First is Portland cement and the other one is Geopolymer cement. Red dotted lines show Portland cement and the green lines show polysilate siloxy cement, and there is a huge difference between Portland cement, as geopolymer cement is much better than the Portland cement. Now we have setting time and hydration rate. Initial and final setting times of cement are used to monitor the hardening rate. The initial setting time indicate how long concrete mix maintain its plasticity. It indicates the allowable time to cast the concrete. The final setting time indicates the time after which concrete loses its plasticity, and it is especially useful for planning surface finishing processes. Both times are related to the hydration process, which can be monitored using calorimeter and measuring the evolved heat. Parameters affecting the degree of cement hydration are summarized as these are some parameters which characterize the degree of hydration and its affection. Then we have concrete maturity. Maturity is an indicator used to predict strength development depending on the curing temperature. The required system based on that concept have been developed. For example, high performance concrete paving software utilized temperature data and the maturity concept to estimate the concrete strength at an early ages. Now we have a crack monitoring. Crack monitoring remain a major concern in the concrete industry, and it is crucial for safety and maintenance cost. Concrete cracks are caused by two effects, that is extrinsic and intrinsic. The former is induced by the application of excessive loads. The intrinsic effects are related to the hardening process and are considered as non-structural. Intrinsic cracks are controlled by the mix design, mixing method, ambient temperature, and also humidity. Now, the highlighted part is about life cycle assessment and environmental impact of cement. These include goal and scope, describe the assessment objective alongside with the system of the product and process. Functional unit, target audience, system boundaries, assumptions, etc. It basically defines the jurisdiction of assumption. The functional unit that will be adopted in this study is 1 kilogram of cement. All dataset analysis and interpretation will take into account dysfunctional unit. This study aims to analyze the environmental impact of 1 kilogram of cement using midpoint and endpoint approaches so as to rightly quantify the level of impact and make proper recommendation. The study will be conducted from candle to gate. Now, life cycle inventory (LCI) stage has to do with the compilation of input and output inventory data that are not only consistent with the product under assessment but equally have several environmental coverages. The database of environmental impact include all emission as a result of the production process. In this study, data modeled after the rest of the world, apart from China, Europe, Switzerland, US, will be considered. Dataset will be taken from the uh, Equipment dataset. Life cycle assessment is a multiple issue tool used to evaluate potential environmental impact that are in line with environmental resources identified in the life cycle inventory. This assessment addresses several environmental issues such as energy, climate change, water pollution, etc., thus allowing for comprehensive evaluation of the impact of product. The LCIA stage is a multi-phased process which group all inventory into their various impact categories. Thereafter, analysis is conducted at the final stage where LCIA and LCI results are interpreted. Interpretation is the last stage is an efficient method used to evaluate, compute, and categorize the result from the information provided by LCI and LCIA and relate them effectively by showing the effect each output data has on each impact categories and consequently establishing the goal of the study. In this phase, production processes and substance with significant impact will be presented in a comprehensive and lucid manner after which proper recommendations are made. This flowchart shows the life cycle assessment framework. These are interlinked with each other and also with the interpretation.